What on earth is a LUT? Now, LUT stands for lookup table, and although it's something that's relatively simple to use, it gets a little complicated when you try and wrap your head around it, so that's why I'm going to try and simplify it as much as I possibly can in this very video. So if you have never even heard of what a LUT is or what it does, the easiest way I can put it for you is imagine it as an Instagram filter, but you know, a bit more pro. I may have just triggered half the film industry. Of course, aside from turning your images into a washout of hipster-friendly colors, LUTs are very commonly used for much more technical and serious processes, such as converting footage that was shot on the log profile to a more common gamma to either be worked on or simply just to make it more comfortable to look at, or when you want to conform an image from one color space to another. So I guess a more textbook answer to what is a LUT would be a set of instructions for remapping pixel values. Also, the explanation that's about to follow might make a bit more sense if you're familiar with what bit defs are. So if you're not quite sure what bit defs are, I've previously explained them in this other video in just under 3 minutes if you'd like to check that out before we move on. So LUTs, there are two kinds of LUTs. 1D and 3D LUTs. So let's start with the one-dimensional LUTs. So as mentioned earlier, LUTs are lookup tables, which are very similar to how we reference conversion tables and look up a value to convert it to another value. For example, this decimal to binary conversion table. So you have an input value of which you use to look up the corresponding output value. Now, instead of converting decimal to binary, an actual imaging LUT converts an input luminance value to an output luminance value. So how exactly does a mathematical table turn this into this? Now, a 1D LUT is actually more like a 3-in-1 LUT because that one LUT contains 3 separate tables, one for each of the RGB color channels. So you would look up the red channel against one column, the green channel against one column, and the blue channel against another column. And now let's assume we're going to apply a LUT to an 8-bit image, which has 256 possible values of luminance. The software is going to look at a pixel, identify its luminance value, and then look up that value on the lookup table, and then find out what the corresponding output value is, then change the pixel's value to that new value, and this repeats for each channel for each pixel. So this process allows the LUT to apply some more simple luminance-based adjustments to your image, such as contrast. For more complex adjustments, that's when we use 3D LUTs. Now, 3D LUTs. It gets quite a bit complicated and brain-frying if you try to imagine it using a list of table values like we previously did with 1D LUTs, so we're gonna use the easier way of visualizing a 3D LUT, and that is with a cube, a color cube. This cube represents the color space of the image, meaning every single possible variation a pixel could be in that image exists as a point somewhere inside this cube. So what a 3D LUT does is move these points from one spot to another spot within that cube. And this process, as some of you may know, is called a transformation in mathematical terms. So that pixel then assumes the color of whatever point it lands on. So just to recap, this cube represents the color space, and every 3-dimensional coordinate within this cube represents a unique color. Now, what I mean by color here is a unique combination of hue, luminance, and saturation values. So now let's put a 3D LUT in a more visualized way. Each pixel is placed in the cube at the exact point where the pixel and the cube's color match. And at every point in the cube, there's a different instruction for each specific point to remap that pixel to somewhere else in the cube, and wherever that somewhere else is, the pixel changes its color to that. Now, the thing about 3D LUTs is, if there was a unique transformation instruction for each and every single possible value that exists on that cube, that will make the LUT file impractically huge. So what they actually do is there is a reduced set of instructions spread out across the cube. So not all values have their own instructions, and these values which do have instructions are called nodes. So then what happens is the instructions for the values that exist between these nodes are calculated through interpolation based on the instructions of the nodes that surround them. Basically, it figures out what's in between based on what's before and after. So this is why when you download 3D LUT files, sometimes you're given multiple LUT files, each the same LUT, but have a different number of nodes per axis. So we can kind of imagine it as the resolution of the LUT itself. The more the number of nodes, the higher quality the LUT. And if you have a LUT with very little nodes, then you might get banding artifacts in your image when you apply that LUT. And with that, it probably makes sense that one of the most common file formats for a LUT file is a .cube extension. So there is my explanation for LUTs. Let me know in this poll right here whether or not this explanation was successful for you, whether or not you now understand what LUTs are. If you found this video helpful and or enjoyed it, do consider subscribing for more videos just like this. Also, let me know in the comment section down below what would you like to hear me explain next. So that's it for today, everybody. Thank you so much for watching, and I will see you in the next video.